we're going to take it one step further. And I think this is kind of cool, but it can get a little tricky here, but it'll come full circle for us. So we're going to say is force times time is impulse. So that's the equation we just jotted down. And then it was equal to m times change in v. Well, you might think to yourself, well, we wrote down that change in v was equal to final velocity minus initial. And you're like, okay, so we just are going to sub that in there, vf minus vi. And for math class, you distribute the m to both terms, so m times vf and m times vi. So what you have here is that mvf minus mvi. And then you're going to say, well, m times v is momentum. And if it has a subscript f right there, that's your momentum final. Minus, mvi, well, that's your momentum initial. So I get pf minus pi. And then you're like, oh, final minus initial, I can use that Greek letter delta. So that's change in p. So what this effectively says is if you look at the very beginning, impulse is equal to force times time, which is equal to m times change in v, which is equal to this, which is equal to this, which is equal to delta p. So Newton basically proves to himself that if you have an impulse acting on something, it causes the object to change its momentum. So that's how he proves that impulses change an object's momentum. And we like this equation because it basically proves I equals delta p. Impulses change momentum. But this is the one we use a ton because an impulse is equal to force times time, and change in p is just whatever the mass is and times the change in velocity. So let's take a look at a few cool examples. All right, so this equation explains so much in life, but I just picked a couple because you can't talk about all examples. But think about when you've been driving at 30 miles per hour, say. How does braking stop your car? Like, what's the physics behind that? Well, all you need to do to figure that out is look at this equation. So if you want your car to stop, that means you want your velocity to change. Because if you're going 30 miles per hour, you want your velocity to change from 30 down to 0. So you basically want to lose 30 miles per hour. Well, mass of your car is not going to change when you're braking unless something's gone horribly wrong, like tires are falling off your car or something. So mass is just going to be constant, right? So the way you can change your car's velocity, there's basically two variables. You have the force you can affect or the time. So picture this, if you want your car to stop, you could apply a huge force, so a very large force over a really small time in order to get your velocity to change. That's not super comfortable for the passengers, like you just slam on the brakes. Or most people when they stop, if they're going 30 miles per hour, they'd say, well, I don't need to apply a huge force over a small time. The opposite would also be true. So you could apply a really small force over a longer time, and you would have the same result. You'd change the velocity of your car. A good example I talked through with my wife, who's a dentist, when you want to move your teeth, when you have braces, the orthodontist could apply a very big force on your tooth for a short amount of time in order to change the velocity of your teeth to move them, right? That would be really uncomfortable. Like, as it is, braces are kind of painful. So you don't want to put a huge force on a tooth because that could really damage the tooth over a short time, although it would be nice because your braces would be off like that. Instead, what they do with orthodontists is they put a small force on your tooth over time. Then your tooth changes velocity, and then they're like, oh, let's put a small force on there again, and they keep putting a small force over a long time. And that's how they move their teeth. You change the momentum of your teeth. All right, another example, cars on ice. In the winter, when you're driving 30 miles per hour, when the roads are icy, for example, why does physics say it has to take longer to stop? Well, in the wintertime, your stopping force that would usually come from your tires and the friction on the road, it's now from your tires on the ice. So this stopping force, if it's from friction, it's going to be really, really small. So your stopping force from the friction of your tires on the road is really small, which that means in order to change the velocity of your car, it's got to take you more time. So the stopping time has to go up. And it's just the physics of the situation is when the friction goes down, when the roads are really icy and the frictional force to stop you is low, the stopping time has to increase. And I know I've done it, I'm sure you have too, where you didn't stop with enough time, and then maybe you slide into an intersection because the physics says it's going to take you this much time to stop. And it doesn't care that you're going to slide into an intersection, it takes that much time. So I just want to show you a couple examples. These are cars, and I forget what state this is in, but it's a state that is not used to driving in the winter. So they don't allow for a big enough stopping time T. And you're going to see is that they just keep sliding objects in motion, stay in motion until acted upon by an outside force. I'm going to mute that. So basically they're trying to stop right there. The brakes are on. And they just rear end somebody because the outside force is the car in front of them. And it just keeps happening. I think there's like 100 accidents at this location. And you'll see this guy's kind of laughing because he's not driving. And notice that's a big Chevy Suburban that starts sliding. This person gets out of their car to try to use their feet like Flintstone brakes to stop their car. I'm not picking on him, but obviously he didn't have this little lesson on how to stop a car. I mean, you're not going to stop it with your feet there, buddy. So because the force to stop him is so low, because the friction's so low, because it's icy, you need a huge time. And it's just kind of sad because it just keeps happening. And then when you rear end somebody, it's your fault. So you're going to see at the very end here, the police get called and everybody who rear-ended somebody, they get written a ticket. Yeah, so it's basically kind of like a big Newton's cradle with cars. That's a bad idea. Never get between two cars. And you get the police and fire come, and then eventually tickets are issued. I wanted to show you one more here. This, again, I think, I'm not sure, it's some place where they don't typically get snow, and it's on a hill. And people are trying to brake, but that frictional force is so low, you need a big stopping time. And so just take a look at what happens here. Objects in motion stay in motion. They have momentum that they can't stop. You think that car is accelerating, but really they do have their brakes on. You'll see when they're going on the hill, they have the brakes on. But since that stopping force is so low, you need a long time to stop. And you notice they collide there and they transfer momentum to that car. You can see the brake lights are on trying to stop, but it just got that momentum transfer. Okay, so this car, you can see the brake lights are on again, so they have the brakes on. And it sounds like they're accelerating, but really this is a slight hill. And they're sliding sideways. I would not be walking around down there. I'd be up wherever this video is being shot in an apartment, so you're safe. I think maybe have one more car that comes through that's a little scary. And it looks like they're accelerating there, not accelerating. Well, they might be accelerating on the hill, but not from stepping on the gas pedal. They're accelerating just because they're going down the hill. You can see their brake lights are on. Momentum transfer. And then an impulse is exerted on that car because it hit another car. We'll kind of finish with this. Changing momentum, airbags, and crumple zones in cars. You might have noticed in our last video on momentum, we had that Ford Explorer that basically crumpled up. And I always get students who ask me, well, why do cars crumple? Is that supposed to happen? And yeah, the front is supposed to crumple. And you are supposed to have airbags in cars now. It's a law. So if you think through that equation we talked about, Ft equals m times change in v, why do you want airbags and crumple zones in cars? And the answer is going back to what we talked about just before watching those videos. You want the time of stopping to be very great, because if you have a crumple zone and the car crumples over a longer time, for example, the time of impact is longer, that means that the force can then decrease. So the force will go down, and that will change the car's velocity. But if you don't have a crumple zone, like one time I had a student say, well, Mr. why do they make cars just out of like straight steel? Like well, that steel, and if it was reinforced like in X's and triangles like the frame of the car, that stopping time would be really, really short or really small. And by doing that, the force would be huge, and that'd put too much force on the occupants of the car. It'd kind of be like when somebody is going to toss you a set of keys, for example. you always give with the set of keys, because if you extend the time of impact, the force on your hand is less. But if somebody throws a set of keys at you and you're not ready for it, and it just strikes your hand, and the time of impact is really small, then the force is really great, and that really hurts your hand. So, yeah, hopefully you took something away from today on momentum and impulse. It's really interesting stuff. I will say, if you haven't taken a look at this review assignment yet, in our white physics book by Paul Hewitt, chapter 8, Momentum and Impulse, is very good, pages 124 to 131. And I would say if you just lightly read it, take away 10 key ideas, write those down, and then try those questions there, you can kind of check yourself to see if you have momentum and impulse down. And then we will definitely use those concepts later in the year as we do our engineering projects like the egg drop, because you're trying to keep your egg safe. So you want to minimize the force on there. So, all right, as always, thank you for watching. Go Physics All-Stars.